Stochastic Finance Seminar. Today is our great pleasure to invite Xiaofei Shi from Columbia University, and she will talk about liquidity risk and asset prices. Xiaofei, please.
Okay, so I guess good morning, everyone. My name is Fei, and you can just basically call me by Fei. And I'm from Columbia University, the stats department. And I would like to thank Professor Liang and Professor Hadding here to invite me here to give a talk on our most recent work on liquidity risk and asset prices. This talk is basically based on several joint work in progress with Agostino Capponi, Lukas Gonon, my supervisor Johannes Muhle-Karbe, and Chen. And the motivation of this study is in practice, when we're trading in stocks or any assets, we cannot really adjust our portfolio willingly, but we have to also consider the cost about doing so. And especially we need to consider how easy the assets we're interested in are traded in the market. So the liquidity is basically a measure for how easy one asset is traded. Our interest is to understand how do liquidity as well as the potential liquidity risk impact on asset prices. For example, we would like to ask, does there exist an yield liquidity discounts, or there's actually liquidity premium? Also, how do the existence of trading costs affect the volatility of the assets? Moreover, we would like to understand how do these existing results change when the liquidity fluctuates randomly over time. For example, we want to know, do higher liquidity fluctuations actually result in higher yield liquidity discount? And to answer all the above questions, we would like to study inside of equilibrium models, where the price level, the return, as well as the volatility to response to the market yield liquidity is actually through the agent's endogenous trading decisions. It's not really from any like exogenous trading decisions. And this means we need to study the equilibrium models. Computing equilibrium models always requires solving some fixed point problems. And this is usually already generally very hard, even without market frictions. And from the literature, we also understand the individual optimization problem also becomes much more difficult with the existence of market frictions. And in particular, the fluctuations of liquidity plays a crucial role in the trading decisions. And
sorry to interrupt you, Fei. So at least for me, I can't see your screen now. So I don't know if everyone can see your screen.
Oh, I mean, this always happens to me. I'm not really sure actually. So hi Martin, can you see my screen? Or
no, I can't actually.
Oh, maybe let me.
It says the recording has started, so maybe is it not related?
Great. I thought I just so
maybe you can stop sharing and share again.
Yes, okay, I think that would be a good idea. Yeah.
I do stop the sharing, and can you guys see my screen?
Yes. Now we can see again. Okay, thanks.
Oh,
yes, thanks.
Okay, great. Oh, that always happened to me during my lectures. So basically, this is just an idea about why do we want to study the liquidity and the potential liquidity risk impact on asset prices, because it's really a very important part in you might have like a really great impact on asset prices, and it also affect the agent's trading decisions. So, and we really want to do that inside of an equilibrium model because we want everything to determine endogenously inside the model. And solving the equilibrium problem is already generally very hard, even without the friction in the market, even without the trading cost. And in particular, if you add in the market friction, then the difficulty only compounded with each other. And and I believe you guys can see this very incomplete list of literature. So basically, people have to, people in history, people are either focused purely on the numerical solution of the equilibrium problem with frictions, or they have to assume some very restrictive Stochastic facts. For example, as in the work of Achaya and Peterson in 2005, they studied a discrete time equilibrium model with the existence of liquidity risk, but they assume the agents are only allowed to trade once after a pre-specified holding time. And in the work of Low, Mamaski, and Wang in 2004, as well as Kim Weston's work in 2017, they assume the assets has zero volatility, which means they only study the impact upon the interest rates. And in the work of Johannes and the work of Bouchard, Fukasawa, Heiding, and Muhle-Karbe in 2018, they study the equilibrium return, but they assume the asset has exogenously fixed a constant volatility. And our work actually follows closely to the most recent work of Heiding, Muhle-Karbe, and Possamai, where, to my best of knowledge, this is the very first continuous time equilibrium model with endogenous volatility on the asset. But they also have to assume that the agent's preferences are sufficiently similar. And based on the same settings as Heiding, Muhle-Karbe, and Possamai, we actually are able to establish the global existence for a specific model with constant quadratic trading costs under the linear state dynamic of the system. And I have to mention, this global existence is without any smallness assumption. And from this solution, we can obtain the rigorous asymptotic expansions for the equilibrium in the limit of small trading costs. And we're inspired by this explicit expansion, we are able to formally derive the explicit small cost asymptotic approximation for not only more general market dynamics, but also with more general trading cost specifications. And that even allows us to account for liquidity risk. And the theoretical results from the small cost asymptotic approximation actually are able to reproduce the Stochastic facts of trading volumes and asset prices. And it can also produce testable implications on the relationship between the trading decisions as well as the liquidity risk. And also on the empirical aspect, we calibrate our model to empirical time series data, and we're also able to reduce compatible results. So without further ado, let me introduce the model we're using. For illustration purposes, we assume the market uncertainty is captured by a one-dimensional Brownian motion. And we assume there are two agents. And in order to give them a reason to trade, we assume they are endowed with a stream on non-tradable risky income with this form, where the income is a martingale and can be expressed using this representation. And these two agents is going to share the risk by trading in one exogenously fixed risk-free asset with 0 interest rate, and one stock with dynamic, the ST equal to mu t dt plus sigma t dwt. We assume the risk-free asset is perfectly liquid. That means you don't have to pay anything if you adjust the position of your risk-free asset, but trading in stock markets are costly. So therefore, we need to assign some preference on these two agents. The preference we take is a tractable linear quadratic model, as in Galliano and Pedersen's work in 2013. So basically, we are maximizing the expected return from the stock market. Again, because the interest rate is assumed to be 0, and with a penalty upon the quadratic variation of my portfolio throughout the time. And also, I need to subtract the trading cost throughout the time interval. And the form of the trading cost you can see here is lambda t over 2 times phi dot t squared, which is basically a quadratic penalty upon the trading rate throughout the interval. And the trading cost parameter is this lambda t process. And they are treated as exogenously fixed. And it can potentially be a stochastic processes. And let me pause a little bit and mention that for the quadratic cost, our result can actually be extended to arbitrary number of agents and arbitrary number of stocks, supported by an arbitrary number of Brownian motions. But for other trading cost specifications, we do have similar results in the limit for small trading costs, but we need to assume that the number of agents is 2. And now it is, let me discuss what is an equilibrium. So we're saying the market is in equilibrium, provided that first, the individual optimality condition is satisfied. That means each agent maximize her or his own individual goal functional, which is a linear quadratic preference we just talked about. And the second condition is a market clearing condition. That means the agent's total demand needs to equal to the given fixed supply outstanding in the market. And then our goal is to determine the expected return and the volatility, as well as the initial stock price inside of the equilibrium. We basically here have 3 unknowns, and we only have 2 conditions. So in order to endogenize the volatility, we need an extra condition. And this extra condition we choose is to choose a terminal stock price that equals the exogenously fixed terminal condition at maturity. And this quantity can be interpreted as a fundamental value or the liquidating dividend. And this is the same endogenous volatility method used in heading, Muhle-Karbe, and Poisson-line. And I have mentioned there exists some other ways to endogenize the volatility, but we do have to add in some extra condition. And now, let me solve the frictionless equilibrium as a comparison benchmark. And in order to first set up a comparison baseline, and also to show you how these 3 conditions are used in determining an equilibrium. So in the frictionless market, basically the penalty upon the trading rate vanishes. And for intuitively, sorry.
Yeah, we can't see your screen again.
Oh, I really don't know how this. I I mean, I really apologize for.
No problem. I mean, you can stop sharing and sharing again, as Labi suggested.
Yeah. So and just please stop me whenever you can't really see it again.
Yeah, yes. Now it's back. Yeah, thank you. Thanks.
Okay. So is it like so basically this is the last slide you see, right?
Yes. Yeah. We
Okay,
can see
great.
it. Yeah.
Okay, so basically now we're in the frictionless market. The penalty upon the trading cost vanishes. So, and intuitively you can think your goal is to choose the optimal position and adjust yourself to that position each time, because there is no cost of doing so. And from the maximization problem, we can see inside of the expectation as well as the integration, this is basically a quadratic form with respect to phi t, that is the optimal position you would like to choose at time little t. And therefore, you can apply the pointwise maximization of the integrand and end up with an optimal position you want with respect to the mu t, which is the return of the stock, and sigma t, which is the volatility of the stock, and as well as the gamma n, and that's your risk aversion. And this is basically the solution of the individual optimization problem. And then the second step you have is now you have the market clearing condition. That means you need to match the total demand of the agents with the total supply outstanding in the market. So therefore, you end up with a relationship of the equilibrium return mu t with respect to the equilibrium volatility sigma t. And let us pause a little bit and see what do we have here. So the mu t bar is equal to gamma bar times sigma t, where the gamma bar is actually the aggregate risk aversion of these two agents, and that means your equilibrium return is basically in a square quadratic relationship with your equilibrium volatility. And here this C1 plus C2 times WT is the two agents aggregate endowment throughout the interval. And now you've already used up these two conditions, so you need a third one to determine the equilibrium volatility as well as the stock. What you have is you know exactly how this stock price evolved as time goes by, and you are provided an exogenously fixed terminal condition. So this characterization is called the backward stochastic differential equation, where first of all, it is a stochastic differential equation, and second, you have a condition that at the terminal time. And so basically with sufficiently integrability of the terminal condition here at the terminal time, you will end up with a unique solution of this SDE within the class of the solution that provided is sufficiently integrable. So let's see a very simple example, and we will be using it as our comparison baseline later on in the discussion. So for C1 plus C2 equal to 0, which means the agent's aggregate endowment is 0, and the terminal condition is linear with respect to the driven Brownian motion, we end up with the Bachelier dynamic for the stock, where you can see here the alpha in front of the WT term and the gamma bar times S times alpha squared term in front of the little t. These are the equilibrium volatility and the equilibrium return respectively, and both of them are constant. And from the literature of the analysis of scalar quadratic SDE, we know this solution is the unique solution to the BSDE among the class with bounded volatility. And now we are going to take a brief look at the equilibrium with transaction cost. So now I'm throwing in the quadratic penalty upon the trading rate. And we can see this problem is immediately becomes no longer myopic, because with trading costs, you also need to consider your current position. It becomes an extra state variable. That is, you have to consider your current position when adjusting your portfolio, and any bad decision you make today, you're going to suffer from it tomorrow. But nevertheless, the individual optimality condition is actually described by the so-called forward-backward stochastic differential equation. So basically, the forward component is your optimal position, and it just evolves forward because you know exactly where it starts from in the given initial position you have. And there is a backward component of the system, and one choice of this backward component could be the optimal trading rate we have, which is the phi dot. And intuitively, you know, it is never optimal to trade at maturity time because the stock price doesn't really have any time to recover from the value where it is at now. But the cost of it is immediate. So this is the solution to the individual optimization problem, and it's already very complicated. And then again, for the equilibrium, first you're going to use the market clearing condition to get a relationship between the equilibrium return as well as the equilibrium volatility. And now, if I have time later, I can show you the derivation of this forward-backward system. And the equilibrium return also has to depend on agent's optimal position as well. And then the terminal dividend condition also yields an extra backward stochastic differential equation to determine the equilibrium volatility. So what you end up with is a fully coupled forward-backward stochastic differential equation system that determines the equilibrium volatility, the stock price, as well as the optimal trading strategies. But unfortunately, the worst term, even with quadratic cost specifications, is linear times quadratic. So unfortunately, no general theory exists for such system. But we do get lucky. We are lucky because under some very special cases and some very special dynamic of the market, we can have an exact solution exists. And we're going to use the exact solution to motivate an approximation in much more general models. So now let us take a look at the special case. Again, in the special case, we have the linear terminal dividend condition. That is, the terminal liquidating condition is linear with respect to the driven Brownian motion. And also we have zero aggregate endowment. Also, I'm assuming the trading cost right now doesn't contain any liquidity risk. That is, it is a constant trading cost throughout the trading time horizon that I'm considering. And recall that the linear state dynamics actually leads to frictionless Bachelier model when lambda is 0. And again, inspired by the work of Hattie, Muhle-Karbe, and Possamine, they apply the linear ansatz to reduce the forward-backward stochastic differential equations to 4 coupled Ricardi equations. Although this is like still a coupled equations, but at least it's ODEs instead of stochastic differential equations. And from there on, they can apply asymptotic expansions for similar risk aversions. What we have is we focus on the Ricardi system, and we realize by a set of changing of variables, we can reduce the 4 Ricardi equations into 2 Ricardi equations. And with some other tricks that is called variation of constant, we end up with a path-dependent, but still a scalar ODE. So we basically can, for this integral differential ODE, we can apply elementary estimations and therefore get the unique solution for the Ricardi equations without any assumption on the trading cost or any assumptions on the risk aversions. And now that we have the existence, and with the existence of the Ricardi system, we are able to establish the existence of solutions. I know it's let me share the slides again. I really apologize for the technical issues. And so basically, now we establish global existence of the equilibrium. What we want to know is whether this simple model can give me some reasonable numbers if we calibrated our model with empirical data. So here's what we do. We took the 10-year daily data of value-weighted Standard & Poor 500 stocks, and so and then we can use this data to estimate the empirical volatility and the average yearly return, and treat these two quantities as the frictionless, the frictionless constant return and constant volatility. And then together with the total shares outstanding in the market, we can determine the aggregate risk aversion of these two agents by matching the expected return in the frictionless baseline model. And now if we want to get the absolute value of the risk aversions of these two agents, we figured the heterogeneity of risk aversion is actually a free parameter. So we choose gamma 2 equals to 2 gamma 1 for illustration purposes. That is, we assume the first agent has twice the risk capacity of the second agent. And then is how we calibrate the parameter for the quadratic cost. So we choose the cost parameter to match the effect of the proportional cost, which is estimated as 0.25% of average stock price as Novi Marcus and Valley Cost work in 2016. And finally, we're going to choose the endowment volatility C to match the average number of shares traded per year. Then with this calibrated parameter, we basically have everything ready for the Ricardi system. And then what we do is we numerically solve the Ricardi equations and then simulate a Brownian path in a 10 years time horizon. And this is our result for the simulation. So on the upper left panel, you see the total share turnover per day, and the blue line is our simulated result, whereas the orange line on top of it is the true trading, the true total share turnover data from the 10-year value-weighted Standard & Poor. And we can see the level of the total share turnover is matched perfectly, although it's a pity that we can't really match the volatility of the total share turnover. And on the upper right panel, this is the difference of the frictional and the frictionless stock price. And again, the blue line is our simulated simulated path for this stock. And the orange dashed line you can see basically shows that this difference of the stock price is in a very good linear relationship with respect to the time to maturity. And in the lower left panel, this is the difference of the frictional equilibrium return minus the frictionless equilibrium return. And we can see that although nothing of our input is assumed to be mean reverting, the existence of the trading cost actually makes the return mean reverse around its frictionless counterparty and is at least in the leading order. And in the lower right panel, this is the volatility change, which is the difference of the frictional volatility minus the frictionless volatility. And we can see basically for a large time, for a long period of time, as long in this 10 years time threshold, only in the last several trading months, which is basically 2 to 3 trading months, you can't really treat this difference as constant. But prior to that, or if the time to maturity is sufficiently large, then we can basically treat the change of volatility as a constant. And these observations from the empirical data really encourage us to study in the limit of small trading costs. And therefore, we expand our Ricardi system in the limit of small trading costs, and this is what we end up with. So first, we realize the change of volatility is basically of order square root of lambda, which is a square root of the magnitude of the trading cost. And then the change of the equilibrium return is first, in the leading order term, it is mean reverse around 0. And that is of order square root of, that is in the order of lambda to the 1/4 power, which is of a higher order. And the expected change of the return is also of order square root of lambda. And therefore, we end up with the change of the stock price is basically also of square root of lambda. And also we can see from the expansion of the change of volatility and change of stock, the return, similar explicit asymptotic results is held if we have gamma 1 and gamma 2 are sufficiently similar. And this is as the same discussion as in Martin heading, Muhle-Karbe and Poison's most recent work. But actually, our small cost asymptotic can actually apply much more generally. And we do try a little bit. And so the first 2 things is what we didn't success when trying this. So we figured no explicit formulas exist if we go beyond the linear state dynamic model. And also, there is no explicit formula available when the liquidity risks are taken into consideration, as in Achaya and Peterson's work. But if we go back to the literature in the discussion of single agent models, such small cost settings is as such, all of these above mentioned settings can be studied in the limit for small trading costs. And here is also a very incomplete list of literature. And we figured the asymptotic expansions in the single agent models can actually work in more general models. So this is our motivation. And then we apply the similar small cost asymptotic for our equilibrium models. And we do figure the formal asymptotics actually works in general with not only general state dynamic models and also allow us to account for the liquidity risk, but it also can work in the general power cost specifications, even including the proportional cost case. But the rigorous verification now we prove is worked out for the quadratic cost case so far. So let me show you our motivation. The first key observation from the linear state model is that the optimal trading rate is, at least in the leading order, linear in the deviation from my current position from the frictionless equilibrium position. And this is, again, similar to Muhle-Karbe work in the discussions of single agent model.
Sorry, Xiaofei, to interrupt you. I think your screen is freezing again. Oh, so now it's back. Thank you. Thanks. Sorry.
Sorry about that. I mean, I am really sorry about this technical issues. I apologize again. So is it better now? Can you
Yes,
guys...
back. Yes, back. Yes, back to normal.
So basically, so at this page is frozen, and now we have. Yeah, we go to the next page. That's
yes. Yeah.
Cool.
Thank you.
Okay, great. And again, sorry about that. So basically, the first key observation is that asymptotically, in the linear state model, the optimal trading rate is in general linear with respect to the so-called fast variable, which is actually the difference of my frictionless optimal strategy subtract my current position. And also, from all the other quantities are either exogenously given, for example, like the gamma 1 and gamma 2, as well as the cost parameter lambda t. Also, or actually from the frictionless equilibrium. For example, this the S bar quadratic variation dt, that is basically the sigma bar squared, which is the frictionless volatility squared. And and at least in the leading order analysis, the difference turns out to be negligible. And also from this asymptotic formula, we can see how the agent timing the market. So if the frictionless volatility is high relatively to the cost parameter lambda t, the agent is going to trade faster. And therefore, we just make this ansatz of this linear structure hold generally, also with any dynamic for our market. Now, what about the equilibrium price? So here comes our second key observations. So first, we expect the leading order term of the price correction is also the order square root of lambda. And this is again inspired by our linear state expansions, as well as in the analysis of the single agent models. Also, crucially, again inspired by the linear model, the fast variable, which is a deviation of the frictionless optimal portfolio of my current position, is actually mean reverting very fast. And also, it should average out at the leading order. And therefore, if we use this, if we assume this answers in the general market, the trading rate and equilibrium prices for small costs can in turn be identified by matching the leading order terms that showed up in the forward-backward stochastic differential equation system. It's like in the analysis of Sonar and Tizzi's work in 2013, where the trading rate is a source term and it is as the second character equation of their work. And finally, if we apply Feynman-Cook upon the leading order changes, we therefore end up with the initial price change in the leading order. And we can see from this complicated expression, although it's very complicated, but all the quantities are either given exogenously, or it is taken from the frictionless model. And this expectation, to point out, this expectation is taken under some p hat measure that's equivalent to our physical measure, and this is due to the use of Feynman-Cug. So now let me return to my very first question. So does there exist yield liquidity discount in the market, or there is actually liquidity premium? The answer is really depends. It depends on whether the more risk-averse agents wants to buy or sell when the stock price goes up. It is really depends on the relationship of the frictionless strategies of these agents with respect to the stocks, the frictionless stock volatility. And this result is similar to the result that had in Muhle-Karbe polysamine. But now, what about the existence of liquidity risk? In Achaya and Pedersen's work, when they study the existence of independent liquidity risk, it actually can make everyone worse off. But in our work, we are still saying it depends, because this time the agents can actually time their trades, and the liquidity risk may increase or decrease the asset prices, and that's really also really very depends on the agent's endowment, the relationship of the agent's endowment volatility, as well as the frictionless stock price and their frictionless trading strategies. And so in the following, we do have another discussion on the numerical solution aspect. We don't really count on everyone work in the investment bank to really write down an analysis a complicated system of forward backward stochastic differential equations. So we do really want to explore about like what kind of numerical solution we can provide. And in this case, we adapt the deep learning algorithm of Han, Jason, and they proposed in 2018. The proposed algorithm is first used for the backward stochastic differential equation, but it can be easily adapted to the FBSDE. This is because the dynamic of the FBSDE system is known if the volatility of the backward components are known. So what you can do is we discretize the time horizon we're interested in. And on each time knots, we parameterize the volatility of the backward components by a comparatively very shallow neural networks. And then we concatenated these networks together, and it becomes deep in the sense that the number of layers of the neural networks is actually linear with respect to the number of discretization of the time horizon you have. And what we can do is then we make an initial guess of all the parameters we have in the system, and then we simulate a batch of Brownian paths forward. And then we end up with a terminal value. And what we do is we just compare to the terminal value through the mean square error, and then update the parameters backward using stochastic gradient descent. And we keep doing this back and forth for several times until the terminal conditions matches sufficiently well. And this method, although it sounds a little bit naive, it actually works pretty well for time horizon that is not too long. And this is our results for the calibrated parameter as a 10-year value-weighted standard poor 500. Unfortunately, this method is only going to work for a fairly short time horizon. And here, for this 10-year data, the time horizon I choose is actually 4 trading months. And we can see on both of these pictures there are actually 3 plots, 3 lines, and the green line is a solution from the exact value through the Ricardo equations, and the blue lines is the solution provided by the deep neural networks approximations, and the orange line is actually the leading order approximation for from our formula. And on the left hand panel is actually the difference of the frictional and frictionless asset prices, and on the right hand panel is the difference of the volatility. So we can see, basically, we are confident to say that my deep neural network approximation can actually gives me the exact solution. And the drawback of the method is I can't really make it work with a longer time horizon. And the reason for that is because even with today's computational power, we're in GPU era. Even with today's GPU era's computational power, we can't really compute a system with more than, say, with maybe 12 trading months or more than a year of the parameters. So that would be too much. And we do thinking about like some other way to accelerate or to further reduce the number of parameters in this setting. And on the other hand, we can see our leading order approximation is comparatively very good if we want to study the approximations. That's a really good next best solution to this approximation. And so this very simple model actually opens a door to a lot of potential areas in this field. So and I'm going to mention several other aspects that's motivated by this simple observations. So first, we can actually work. So these same approximation, explicit approximation formulas can actually works for general cost specifications. That is, without like a quadratic penalty upon the trading rate, we can apply a power, a super linear but subquadratic penalty upon the trading rate. And this power cost is first proposed by Green in 2003, and is widely studied by a lot of colleagues working in this area, including Professor Hadding here. And also, our work can even be generalized to the proportional cost case, where instead of the trading penalty upon the trading rate, the penalty is really on the total variation of your strategy. And in this singular limit, we do have a bang type of control. So it's no longer a regular control, it's a singular control. But we can also observe a similar qualitative effect as in the quadratic cost. So which is a justification for us to use the quadratic cost specifications. And also another thread of the current work I have with my supervisor, Johannes, is we are going to discuss like a more sophisticated utility functions, like the exponential utility as well as power utility. And although this consideration of exponential utility makes this problem at least exponentially hard, but we do really get a lot of inspirations and because we can actually separate the effect from the fast variable and also the effect from the change of the volatility. And another current work we have is we can in the quadratic cos case, we are able to expand our work for multiple agents and multiple stocks. And also, we can explicitly see the mean field limit of such discussion. And I will say, although this our work is comparatively use like a very simple linear quadratic preferences, but we do open doors to a lot of more sophisticated cases. And basically, that's all I would like to discuss for our work. And thank you guys for your attention. And I really apologize for this technical issues.